Hi everybody, welcome to my talk. Let me first thank the organizers for inviting me and no less for organizing this workshop in so difficult times. I want to talk about Fourier restriction for hyperbolic surfaces, and what I'm going to talk about is joint work with Detlef Müller and Vargas. So since this is a restriction workshop, I can be brief on the restriction problem. So we start with a smooth compact hypersurface. We assume to have non-Winchian Gaussian curvature, and sigma will denote the surface measure. Then the extension operator, which is the adjoint of the restriction operator, is this EF, which is just I take F multiply with the sigma, and then I take the Fourier transform. And the restriction problem asks for which values of P and Q the extension operator bounded from LQ of the surface S to LP in R3. And this was formulated by Stein in the 70s. And he conjectured that this holds true if and only if P is bigger or equal to 2Q prime and P is bigger than 3. Of course, in 20 minutes, I cannot tell you all the results and progress in this area. So I just want to mention a milestone from my point of view. This is the recent polynomial partitioning method, which was introduced by Larry Goose. And this allows to verify the conjecture in the range P bigger or equal to 2Q prime if P is bigger than 3.25. And of course, there was some improvement by Hong Wang, but we will use the basic polynomial partitioning method, which was introduced by Goose. So we also get a result in this range. So this was for the case of positive Gaussian curvatures, for instance, the sphere or the paraboloid. And now we want to focus on the case of negative Gaussian curvature. So surprisingly, despite a lot of progress in the case of positive Gaussian curvature, for the case of negative Gaussian curvature, apart from the surface z is equal to x times y, not much was known. Okay, so yeah, we will assume locally we can assume S to be the graph of a function phi, and by compactness it's enough to consider these local parts of the surface. And phi, we can also assume that phi of 0 is 0 and the gradient of phi is 0 as well. And that the Hessian matrix of phi is close to 0, 1, 1, 0, which is the negative curvature. And also technical condition, I want to have some control about higher order derivatives of phi, at least up to some order capital M here. And our result is as follows. So we can show that the extension operator is bounded if P is bigger than 2Q prime. So maybe we miss the critical line here, and we also get P bigger than 3.25. And yeah, so I should mention, so there is the unperturbed case. So you see that this phi of xy is x times y. And this more general phi above here would be x times y plus a perturbation term in the above sense. So that was known by Zhou and Li, and so the thing why the unperturbed case is usually easier is that you can here scale independently in x and in y, and of course if you have a perturbation that breaks down somehow. Well, then this is like the last result in a series. So we started with very simple perturbations of the hyperbolic paraboloid, like the perturbation x cubed, which sounds very simple, but indeed reveals a lot and can also be easily generalized to finite type perturbations in one variable. And well, this is the final result here for general perturbations. And I should also mention that Xiaoming Guo and O independently obtain the same result So I think by some quite different method. Okay, of course I cannot tell you all of the proof in 20 minutes. Even the polynomial partitioning method to explain would require much more time. So I will focus on some key insights and tell you a bit about the geometry of the problem. And well, so one key ingredient, one key feature in restriction theory is transversality. So if you test your extension operator on the characteristic function of such a cap theta here, which has side r to the -1/2, then the extension operator of chi theta basically up to Schwarzschild lives in such a tube which has length r, and the direction is the normal to the surface on theta. And this constitutes the so-called netbox example, which exactly gives this necessary condition that P has to be bigger than 2Q prime. So now if you look at the bilinear operator, so now you take the average of the extension operator applied to different caps here, and imagine the caps belong to two different surfaces, or let's say could be two parts of the same surface, but you have transversality, which means that the normals of the two surfaces, they point in different direction. So you get this formula again. You have these tubes here, but now if the surfaces are transversal, the intersection of the tubes is much smaller, and that helps. So you cannot have a netbox example here. And actually, for the proof, we need some more involved form of transversality, but I will not tell you what this is geometrically. So in the formula, it's the following quantity you need to control to have this kind of desirable transversality. So you take the inverse of the Hessian of phi evaluated at either Z1 or Z2, then you apply it as a quadratic form to the difference of the gradient of phi at two different points, Z2 and Z1. And so imagine we break up our unit square where the function phi lives into caps of side k to the -1, k imagine being a big constant. So we break it up in these chunks, and then you so we call them strongly transversal. If this quantity gamma I is bigger than k to the -2, so we have some bound from below on this quantity gamma I, and this is favorable. So this allows you to prove some good restriction estimates. So I will not tell you anything about what you do if you have this kind of transversality, but I will tell you a bit about what you do if you don't have this bound from below. So what do you do with the other caps here? So there's a very useful factorization. So you can factor gamma I into these two functions T1 and T2, which are given by these formulas. With these terms B and A of Z are some functions depending on the second derivatives of phi, which I will not write down explicitly, but there's proportional to the second derivative solely in y, or the xx derivative. And since we are in the hyperbolic case, both these numbers are small, so you can consider these second terms here as perturbation terms. And in particular, if you look at the unperturbed case as a toy model, x times y, then you see, of course, these second order derivatives here, they vanish. So A and B are 0, and these terms doesn't show up, and you can see that these two factors here, T1 and T2, are nothing but y2 minus y1 and x2 minus x1. So you get a very good idea what this gamma I actually is. Okay, so what about the general case? So let's assume now that we don't have transversality. This means that let's assume that T1, the minimum of T1 and T2 with subscript Zi, that these are less than k minus 1, because if the converse is true, that would mean that both these quantities have to be big, and that would mean that their product gamma, which is gamma I, is bigger than k to the minus 2, so we would have transversality. Okay, and let me make some additional assumptions here. So without loss of generality, let's say we assume y2 minus y1 is bigger, or it could be also equal here, bigger or equal x2 minus x1. And then I also can assume that y2 minus y1 is not too small, so say bigger than k to the minus a quarter, because again, if the converse here would be true, that means both the x difference and the y difference is small. That means both caps tau 1 and tau 2 are contained in a bigger cap of size k to the minus a quarter. So, sorry, I forgot to mention this point Z2 and Z1, they're always the centers of these caps tau 1 and tau 2. Although these conditions are somehow stable under changing the center point to an arbitrary point in the cap. Okay, so under these assumptions, one can check that indeed, like in the unperturbed case, the T1 subscript Zi, this is comparable to the difference y2 minus y1. And we just assume that this is big, so certainly this is bigger than k to the minus 1. And if the minimum of these two numbers is small, that means that the T2 subscript Zi of Z1, Z2 have to be smaller than k to the minus 1. And then, of course, you can also consider the difference of these two, where you plug Z2 or Z1 in the subscript. And you see here, so the first term, that doesn't depend on the subscript Z, so that cancels, and you get a difference of A evaluated at Z2 and A evaluated at Z1. And again, this remaining term here, which is the same in both expressions, again, you can see that this is comparable to y2 minus y1. But again, this is not too small, so you can conclude that A of Z2 minus A of Z1 is less than k to the minus 3/4. These are the two information we have to remember. So the difference of A evaluated as these 2 points is small, and then say T2 subscript Z1 is also small. So think of Z1 being a fixed point and A1 the value of A at Z1. Then we have to understand the set of all points Z, which I now denote, which was Z2 before. So the set of all points where the curve T of Z, which is T1 subscript Z1 evaluated at Z1 Z, is small, and we can be a bit generous here and look at the set where this is even less than k to the minus 3/4, since this is the bigger of the two quantities. And then we also know that A of Z differs from A1 also by at most k to the minus 3/4. And what one can easily check, since we have some explicit formula for T1 Z1, that as long as we are on the set here, the tangent to the curve T at the point Z is basically this expression here up to an error k to the minus 3/4. So basically the curve goes into the same direction. And so this is how this may look. So the green set here is the set where A of Z minus A1 is small. So that may look quite wild. And then the blue line here, this is a curve where T of Z is equal to 0. And indeed, the set where T of Z is small has to be a neighborhood of this curve. And as long as we are in this green set here, more or less this curve goes in the same direction, omega, which is minus A1, 1. And if we leave the green set here, then the tangent may look different. So we don't know what's happening. But if we re-enter the green set here, then again, we have to go in this fixed direction. So as long as we are in this intersection of the two sets here, well, these intersections have to look like these rectangles here, which have thickness at most k to the minus 3/4, direction omega, and well, the length actually we don't know. But yeah, we thought a bit about this point, and well, it depends on what this function a look like. Remember, a contains some second order derivatives of the function phi, so it depends on what kind of perturbations you have. But at the end, that was some crucial point. We realized we don't really need to know how long these rectangles are. So you just pick the rectangles. You take a rectangle as long as you are in this green set, and once you leave, that's the end of the rectangle. That's it. So let me say what we got so far. So any cap T2, which is not strongly transversal to the cap T tau 1, has to be contained in such a rectangle of direction omega, thickness k to the minus 3/4. And we also need to remember that on this rectangle, the value of a doesn't differ too much from a1. And this allows us to do a decomposition of the unit square where the function phi lives. So first we decompose with respect to the value the function a takes, right? So we let aj vary in steps of size k to the minus 3/4, and then we look at these sets where a of z is close to aj, and these sets may look quite wild, right? I mean, the sets, they don't have to be neighborhoods of nice curves or something. They can look quite arbitrary. So for instance, if we go back to the toy model, phi is equal to x times y, then a is identically 0. So you don't even get a decomposition, but just a whole set. But okay, in general, you have this decomposition. And then inside each of these sets, you decompose into rectangles of in this direction of thickness k to the minus 3/4 and maximal length. So it may look like this. So I try to draw this here. The green lines are the level sets of A. So in between, this corresponds to these sets here between the green lines. And then these sets we decompose into these rectangles. And you see, if you change the green sets here, then the direction may vary from set to set. You also see you may get something like here, that you get almost a whole strip, but it may as well be like here, that the strips is cut into several rectangles, maybe two, maybe even more. But well, okay, you get a decomposition of the unit square, and then of course you have to do the same in the symmetric case where y2 minus y1 is less than x2 minus x1. Okay, but what do you do with this decomposition? So important ingredient of the polynomial method is the so-called broad part. So a point is called broad if so I take f and truncate by the characteristic function of such a strip L. So this strip L is the set of all my rectangles, and if the extension operator applied to this part of f is considerably smaller than the extension operator applied to all of f, then we call it broad. So you can see it this way. So if you are a non-broad point, that means the converse is true here. Basically, up to this k to the epsilon error here, yeah, f behaves as if it would be supported in this strip here, the strip L, and the strip L is a much smaller set than the whole unit square. And this allows you to use an inductive argument and scaling. And I will not tell you everything about this inductive argument, but a little bit about what happens with the scaling, what kind of difficulties you encounter. Okay, so first what you do is you move the rectangle L to a vertical position. So these are the first two pictures here. So there's some rectangle with direction omega and thickness k to the minus 3/4, and by some affine transformation, you move it to the origin and you put it upright, so you get a different function denoted by twiddle here. And then you, in the second step, you scale this to the unit interval. So that means you scale in x here by k to the minus 3/4. So this is basically the anisotropic scaling, where you scale only in x, right? And you see if phi is just x times y, then of course this scaling here just cancels out. But now you have some perturbations, and this is a bit tricky. So if you take second order derivatives, if there's one derivative in x at least, you get a k to the minus 3/4 in front, which cancels this factor here. So this is fine. But the problem is the second order derivative in y here, because, well, then you can not get rid of this factor k to the 3/4 here so easily. So a priori, this factor here might be big after rescaling, and yeah, then you cannot deduct because you don't have the bounds you need on this scaled function. So, well, we have to remember there's another property of this rectangle, not just the direction and the thickness. Let's go back a slide. So we have this property that the value of A is essentially A1. And so what one can see easily is that this vector omega is a null direction of the second derivative of phi evaluated at Z1. That's not so surprising, because remember A1 was the function A evaluated at precisely this point Z1, and the function A has something to do with the second order derivatives of phi, which are the entries of the Hessian, so it's not so surprising that you can compute this formula here. But now remember, on L, A of Z is almost a 1 up to a certain error. So you can see that if you change Z1 to Z here, and Z is an L, then you get this quantity as, well, maybe not 0, but less than k to the minus 3/4. And this is nothing but the second order derivative of phi in direction of omega. And of course, what happens now if you do this first step here, you put it in upright position, the omega becomes the y direction. So this just means that the second order derivative with respect to y of the phi twiddle is smaller than k to the minus 3/4. So somehow you can, by this means, bound this quantity by 1, and then by some technical tricks, you can even bound this by a small constant C0. But I will not go into details here. Okay, so this was the non-broad parts, which you can just do by induction. So what do you do with the points which are broad? So recall we started with the fixed cap T1, and then we look at caps T2. If they are transversal, fine, then we can somehow exploit the transversality. What do we do with the non-transversal caps? So we learned they are contained in these certain rectangles, in the family of all these rectangles I call script L of tau 1. So that's some subfamily of all rectangles L. And broadness now means that, well, basically that's a contribution by F in this rectangle L, that this is considerably smaller than the operator applied to all of F. And so somehow that's the idea, that we want to, we put these caps into these rectangles, and the rectangles are considerably smaller. So we do something like a bootstrap argument. And of course, well, we have several rectangles. So what you gain here is k to the minus epsilon. You have to take care that you don't get rid of it again by having too many rectangles. So you want that the number of rectangles in this family L of tau 1 is a number which is much smaller than these quantities, so that you can bootstrap. So of course this is criminally overly simplified, so the actual argument is much more involved. But yeah, this is somehow the basic idea. So everything what I can tell in such a brief time. So okay, how do you call the amount of these rectangles? So here's the picture again. So basically what we have to do is we go along this curve t of z equal to 0, and we check how often do we enter this set where this green set here where a is comparable to a1. So we can do it in the following way. If we parameterize this curve t of z equal to 0 by gamma, and yeah, let's call h of s the function which I wrote here. So what does mean is being in this green set just means that h of s is smaller than k to the minus 3 over 4. So basically, I repeated here the notation. So basically what we have to understand is yeah, the set where h is less than k to the minus 3 over 4. The naive question would be, how many connected components can such a set have? And of course, you can fastly draw a picture, which is not so nice. So it might be that h just oscillates very fast around this value, k to the minus 3 over 4. Then, of course, you get a lot of these connected components. So that doesn't work. But actually, we could use a lemma from some previous work where we studied flat one-variate perturbations. So this is the following. So we have now h is some Cm function on an interval j, and lambda is some level. So think of lambda being k to the minus 3 over 4. Then we can find a family of disjoint intervals, such as the following holds. So the first condition just means that this family script I of intervals is not too big in terms of lambda. And secondly, well, these are not the connected components, but they cover this set where h is less than lambda, and they are contained in the set where h is less than 2 lambda. So you see in this picture, if this very fast oscillation happens here, then well, the function is getting bigger than k to the minus 3 over 4, but not too much bigger. And this is somehow, yeah, what's going on in this lemma. So you need to modify your decomposition a bit to accommodate this factor 2 here, but that's not really a problem. And so the first condition in this case, where lambda is k to the minus 3 over 4, that means that lambda to the minus 1 over m is k to the 3 over 4m, so the m should be in the denominator here as well. So if you choose the capital M big enough, you can make this much smaller than, say, k over epsilon over 2, which is what you want. And that's all I want to say. Thank you very much.